Hello everyone, this is Daniel Stigman, and today I will be covering a KTANE module tutorial. Today it will be the module Decay by Obvious. So let's get started. Just make sure I'm recording.
All available experts, please report to room A9.
Yeah, I'm recording. Okay.
This is the story of a man named Stan.
So this is Decay. This is how it looks. It is a obsidian plaque looking module, partially see-through and reflective, with an animated status light and a little particle array. Very good looking module in my opinion. On it is 3 interactable glyphs. These will be made up of 2 things. They'll be made up of vertical bars and horizontal bars. Each glyph will have 1 horizontal bar each, that will never change. But each glyph can have anywhere from 0 to 3 vertical bars. And each vertical bar can either be connected to the base or not connected to the base. And these connections will give us 2 pieces of information. The first piece of information is the binary representation of these vertical bars, where a bar that is connected to the base is a 1 and a bar that is not connected to the base is a 0. In this case we have 1 0 0 1 1. Hang on. So let me quickly note that down in my manual. Sorry, I'm in a bit of a mess. 1 0 0 and 1 1. Oh, 0 1 1. Additionally, we are also going to note down the amount of vertical bars shown with these. So we have 2 vertical bars here, 1 here, and 2 here. So let's note these down. We have 2, 2, 1, and 2. Let's convert these from binary to decimal. 1 0 is 2, 0 remains 0, and 1 1 is 3. And now what we're going to do is we're going to raise these 2 values as exponents in the equation 2 to the power of k minus 1, where k is these values. So 2 to the power of 2 is 4, minus 1 is 3. Let's do that for these values. And 2 to the power of 1 is 2, minus 1 is 1. So this value will remain the same. And then from here, we're going to just take the sum of each of these pairs. So 2 plus 3 is 5. 2 plus 3 is 5, 0 plus 1, 2 plus 3 is 5, 0 plus 1 is 1, and 3 plus 3 is 6. This number right here is a number that is shown in base 15. Hang on, what is that doing there? I think diffuse has been on my PC, SMH. Welcome to Britain. No, I'm kidding. This number is a number that is represented in base 15, and we need to convert it to base 10. So in order to do that, what we're going to do is we're going to get our calc. Who's been writing in my... for crying out loud. Who's been writing in my PC all these stupid messages? Death. Okay. Get rid of whatever the hell that is. Just put something random there. Right. Moving on. We need to convert this number from base 15 to decimal. So we take the number in query, the most significant digit, and we multiply it by a number where the coefficient is our base, which is 15. And the exponent is the amount of digits that belong to the right of the digit in question. So this will be 5 times 15 to the power of 2. And we're going to do the same for each digit. Plus 1 times 15. Plus 6. And this gives us a number of 1146. That's our number in decimal. It's important to note, do not click any of these buttons, especially not the left or right buttons, as this will take you into submission mode. And we don't want to go into that until the very end of the module. So just leave these buttons alone for now. Don't press them. We'll get back to those later. Probably in about 20 minutes time or something. Anyway, what we need to do now is we need to create a prime factor tree. And to create this prime factor tree, we need to make it out of nodes. This tree can be made in one of three ways. You can either use Notepad, like I'm going to use for this tutorial, or in order for better visualization of the tree, you can use pen and paper, or you can use Paint. For the purposes of this tutorial, I'm going to demonstrate the hardest of the bunch to write it in, and that'll be Notepad. So the way I like to do this is I like to create the nodes with square brackets, and then fill them in with a semicolon, and then there will be three properties. The first property outside of the square brackets will be a number of dashes, and this number of dashes will mark the generation of the node in question. In this case, this is the starting node, so this is generation 0. And inside it, the left number before the semicolon will be a prime factor. These prime factors I will explain shortly, but for the purposes of this first node, we're going to use 0. And then the right number will be the result of a division using this number, but because this number is this is the first node, we're just going to put in the starting number 1146. Now for this, what we need to do is we need to create a prime factor tree with every value, and write each of the children down from lowest to highest of their prime factors, in order from lowest to highest, and they must be unique prime factors, excluding the number itself and 1, because otherwise that will result in an infinite tree, which is what we don't want. With this, we need to take our number 1146, and we're just going to express the number as the product of its prime factors. In this case, we have 2, 3, and 191. What this means is that this node here has 3 children. The 3 children in this case, this is a generation 1, so that's why I'm marking each of these with 1 dash, because they are all children of this node. And with this, we need to put in our first values. The left value, like I said, is the prime factor itself. So 2, 3, and 191, ordering them from lowest to highest. Hang on 1 second. And I'm back, my apologies. So what we're going to do is we're going to take our starting number and we're going to divide it by the prime factor that we obtained. So we're going to take 1146 and we're going to divide it by 2, and this gives us 573. This number will be the result here. It'll be our right number, but not quite. For each of these, we have to add 1 to them. So we do the division and then we add 1 to it, and this will give us 574. For each one of these right values, we have to check if it is prime or not. If it is prime, that means that this number, when we do any division, the only prime factors will be itself and 1, which results in an infinite tree. So for the purpose of this module, any numbers, any divisions that result in a prime number, or any divisions plus 1 that result in a prime number, will be considered as having no children, and we would mark them with an asterisk to denote that there is no children under that node. But 574 is not prime, it will have children, so we're going to get rid of that. And then we're just going to repeat this division process for the other 2 nodes. So 1146 divided by 3 is 382, plus 1 to that is 383. 383 is prime, so that means that it has no children, so we're going to mark that with an asterisk. 1146 divided by 191 is 6. Add 1 to that is 7. 7 is prime, so we're going to mark that. Now, these two have reached the end of their tethers. They do not have any children. So, this tree, this parent, only has one child that will have children. So what we're going to do with this is we're going to nest into it, and we're going to take its number and plug it in. This in itself also has 3 prime factors, just like its parent. These prime factors are for generation 2 under this node. Let me just put this back. No, am I still recording? Yeah. This will have 2 nodes, 3 nodes rather, all under generation 2 with nested within this node here. Let's order them from lowest to highest, 2, 7, 41. And we're going to repeat the division process. So 574 divided by 2 is 287. Add 1 to that is 288, which is not prime. 574 divided by 7 is 82. Add 1 to that, it's 83, which is prime, so we'll mark that. 574 divided by 41 is 14. Add 1 to that is 15, which is not prime because it is divisible by 3 and 5. With that done, what we need to do now, because there are multiple nodes that can have children, you can work on them in any order, so long as its children are ordered in lowest to highest VP, where VP is the prime factor in questions. However, because I'm working down in this tree, I'm going to start with the highest one that has not had its children generated, which is this one here. This node will have however many children I can get out of this prime factor. So I'm just going to generate 2 real quick. 288 has 2 children, 2 and 3. I say 2 and 3 because for the purposes of this module, only take the unique prime factors. So 2 and 3. 288 divided by 2 is 144, plus 1 is 145, which is not prime. 288 divided by 3 is 96, plus 1 is 97, which I believe is prime. Yep, it is, so we can mark that. Then let's plug 145 in, and we get the numbers 5 and 29. That's 2 children. Now, a little trick I learned with this. Let's put the 5 and 29 in first. 5 and 29. So, when you divide your number by one of the prime factors, if the prime factors of this number are all unique when you put it into this calculator, if they aren't duplicated and there's only 2 of them, then what you can do is when you would make your division, the result would be the other prime factor. So all you really have to do is just take the other prime factor and add 1 to it, and that would be the result of the division. So if 145 under the prime factor of 5 would make its other prime factor 29, because 145 divided by 5 is 29, plus 1 is 30. And the same goes with this. 145 divided by 29 is 5, plus 1 to that is 6. Let's generate for 30. 30 should have 3, yep, so 3 children for this. Two, 3, and 5. 30 divided by 2 is 15, plus 1 is 16. Oops. 30 divided by 3 is 10, plus 1 is 11, which is prime. And 30 divided by 5 is 6, plus 1 is 7, which is prime. 16 is 2 to the power of 4, so it only has 1 prime factor, and that's 2. 16 divided by 2 is 8, plus 1 is 9. 9 is equal to 3 squared, so 3 is its only prime factor. 9 divided by 3 is 3, plus 1 is 4. And 4 is equal to 2 squared, so 4 divided by 2 is 2, plus 1 is 3. Mark that. Let's go down the list and find the next one in order that has not been had its children generated. which is this one. 6 has only 2 prime factors, 2 and 3. They multiply together to make 6. So 6 divided by 2 is 3, plus 1 is 4. And 6 divided by 2 is 6 divided by 3, sorry, is 2, plus 1 is 3, which is prime. And then 4 once again is 2 squared, so we can just generate this again, 2, 3. 15 is, it has 3 and 5 as its prime factors. The prime factors of 15 are 3 and 5. So, with this, 15 divided by 3 is 5, plus 1 is 6, and 15 divided by 5 is 3, plus 1 is 4. Let's start with this over here. 6 divided by 2 is 3, plus 1 is 4. And 6 divided by 3 is 2, plus 1 is 3. Mark that. 2 divided by 4 is... no, sorry. Why did I say 2 divided by 4? That would be a half. 4 divided by 2 is 2, plus 1 is 3. And that's because 4 is 2 squared. And then once again for this node here, 4 divided by 2 is 2, plus 1 is 3. And that is the end of the tree. And it took me 16 minutes. Ooh. A long time. And this is like half of the module right here. Making this tree. Now that we've made this tree though, what we need to do, or what I'm going to do now is I'm going to space these out a bit, then do it in a more clear area, so just give me one moment while I do that. There we go. Cool. And what I'm going to do now is I'm going to go back to the module, and this time we're going to press the middle button. What this will do is this will play a 7-tone sequence which we need to get the order of. We need to get the pitch of each of the tones. Now luckily I can explain some things here. The first pitch you heard is the highest pitch that this module will produce, which is a high C. And that last pitch that you heard is the lowest pitch that this module will produce, which is a low C, or on an actual piano, a middle C. And in between that are 5 more tones. This module will produce every tone at least once, so we're going to get a string of 7 numbers from 1 to 7. The starting number, as I mentioned, is 7, and the ending number is 1. Because that's the highest tone that was played first, and the lowest tone was played last. And now I just need to listen to the rest. So what we have to do with this module here is we have to take the gaps between 2 notes, and if the following note is of a higher pitch than the note before it, we make a 1 in our binary string. And we started off with by analyzing the second and comparing it to the first, and then we do the same for the third to the second, and then the fourth to the third, the fifth to the fourth, the sixth to the fifth, and the seventh to the sixth, and the first to the seventh to get a 7-bit string. So what I'm doing is I'm getting each of the pitches, and we can compare from the notes. That was a 4 and a 2. I think that was a 6 in the fourth one. Yeah. And it was just kind of descending from there. There we go. With this, let's compare the pairs. 4 is lower than 7, so that's a 0. 2 is lower than 4, 0. 6 is higher than 2, so that's a 1. And then from here it's descending, so we can do that. 5 is lower than 6, 3 is lower than 5, and 1 is lower than 3. But 7 is higher than 1, so that is a 1 for that last bit. Now, what we need to do is we need to make another binary string, which starts off with the first bit in this string, which in our case is 0, and then the first 2 bits reversed, and then the first 3 bits reversed, so 1, 0, 0, then the first 4 bits in reverse, 0, 1, 0, 0, the first 5 bits in reverse, 0, 0, 1, 0, 0, the first 6 bits in reverse, 0, 0, 0, 1, 0, 0, and then the entire thing in reverse, 1, 0, 0, 0, 1, 0, 0. And we append all these together and concatenate it into one big binary string. Now we need to count, what we need to do is we need to assign these bits to, not all of them, but we need to assign some of these bits, starting with the first bit, and we need to assign them all the way down the tree to each node in order. Each node that doesn't have any prime factors, aka these ones right here that have no children. So let's count up how many nodes have no children by counting up the asterisks. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 nodes. So let's grab these 4 and these 4 and these 4, the first 12 bits. And we're just gonna move these bits over here. We're not gonna need them just yet, but we'll need them for later on in the module. Just 1 second. And I'm back. Sorry about that. What we need to do is take these bits that we have down here, and we need to assign them to these in order. So let's assign the first 4 bits going down the tree. 0, 0, 0, 1. And then another 0, 0, 0, 1. And then the last 4 are just zeros. It is important that you don't delete these bits. Just keep them there for now, because you might need them again later on. It's unlikely, but you may need them again later on, depending on how this goes. Now, what we need to do, starting from the bottom of this tree, starting from the lowest node that doesn't have one of these zeros or ones, we need to look at its children, and its children with the tree spread out. Look at the node's generation, in this case 3. That means its children will be in generation 4, but the way to tell where the children cut off for this node is when you come across another node while you work down that is of its generation or an earlier generation. So in this case there's a Gen 1 right here, so that means that it ends here, and the only Gen 4 in between these two is this node right here, which its bit is a 0. What we need to do is, for each of the children and its bits, we need to go up to their parents and give them bits based on their children's bits, where the equation is you add up the bits together and you take it modulo 2, like an XOR. So we add up the bits of its children. There's only one child and it's given a 0, so this bit gets a 0. Let's go up to the next one that hasn't been assigned. This is a Gen 4, and the next, so its children will be in Gen 5. The next Gen 4 is down here, so it only has 1 children. But its child is a 1, so this gets a 1. Because 1 is itself. The sum of 1 and nothing else is 1. This one is in Gen 3. So that means its children are in Gen 4, and we need to work through until we come across one of its generation or later, or earlier, sorry. So this is Gen 4, so that's one of its children. This is Gen 5, so it's not one of its children, but we can keep going. This is Gen 4, so it is one of its children. Aha! This is Gen 3. So that is our boundary. All the Gen 4s within this bracket, that's this one and this one. The sum of their bits is 1. So this gets a 1. From here, this is a Gen 2, so we're looking for every Gen 3 between it and another Gen 2 or earlier. That would be this, and then this is Gen 1. This is Gen 1. So it's these two here. 1 and 0. And that makes 1. This up here is a generation 5, and there's another Gen 5 right here. So we're just looking at this node. This node right here will copy up to this node. So 1 copies up to here. This is a Gen 4, so its children are in Gen 5. This is a child right here, this is a child right here, and this is a Gen 3, so that's our stopping point. 0 plus 1 is 1. This node right here only has one child, that's this node here, which is a 0. Again, this node also only has one child, so that's which has its binary value at a 0, so that's a 0. This node right here also only has one child, so that's a 0. Or rather, the Gen 6s within this bracket, because here's a Gen 5 and here's another Gen 5. The Gen 6s are its children within here, and its children form to a sum of 0, so it gets a 0. This is a Gen 4, so we're looking for every Gen 5 in here. That's this one here. This one here, this one here, and here's the stopping points, because this is also part of Generation 4. Its children are here, here, and here, and they sum to 0 as well, so bam. Now we're looking for every Gen... This is a Gen 3, so every Gen 4 is here, here, and that's that. So between these... this is a 0, and this is a 1. 0 plus 1 is 1. This is a Generation 2, so we need to look at every Generation 3 between itself and the next Gen 2 or earlier. That would be this, and here's Gen 2. So there's our stopping point. Take the innards, we have here, and that's 1. It's 1. Plus 0 is 1. And for the last node, this is a Gen 1, so we need to look at every Gen 2 in between, up to the next one. So here, here, and here's the boundary. So the sum of these, we have a 0 here, a 1 here, and a 1 here, and they sum up to make 2. Like I said, with these sums, because this is binary, we need to take this modulo 2. So this is in fact a 0. Now, for this node here, we don't take the sum of the 1s. What we're going to do is we're going to exclude it from this. This is not given a bit. Now, what we need to do is we need to work back down the tree, starting by assigning this node a 1, and we need to XOR this bit, the second bit of the parent, with the first bits of each of the children. So let's find the children of this node. The children of this node are here, here, and here. Those are all the Gen 1s. 1 XOR 0 is 1. 1 XOR 0 is 1, and 1 XOR 0 is 1. So they've got their bits. And then we work down the tree. So find the children of this. That's this one, and this one, and it ends here. 1 XOR 1 is 0, so that's this one XOR this one, and that makes 0. This 1 XOR to this 0 is 1, and with this one it becomes 0. Then we work from here, from this node, find its children up to here, here, and here. 0 XOR 1 is 1, and 0 XOR 0 is 0. Then from here, find its children. 1 XOR 0 is 1, and 1 XOR 1 is 0. Then find its children, find this guy's children, right here, here, and here. And for all of these, 1 XOR 0 is 1. This guy only has one child right here. 1 XOR 0 is 1. Once again, 1 XOR 0 is 1. And once again, 1 XOR 0 is 1. This guy right here has 2 children, right here and here. 0 XOR 1 is 1, and 0 XOR 0 is 0. This guy right here has only one child, and that's here. 1 XOR 1 is 0. This guy here has children here and here. 0 XOR 1 is 1, and 0 XOR 0 is 0. The children of this one are here and here. 1 XOR 1 is 0, and 1 XOR 0 is 1. 0 XOR 1 is 1 for this child here. And then this 0 XOR this 0 is 0. And now we've done the back propagating step, let's get our calculator open, and we're going to make 2 numbers. This is the next part. We're going to make 2 numbers. The first number will be the sum of every prime factor in the tree. So let's go through and calculate the sum of all of our prime factors. So starting with this one here, that's 2, plus this one is a 2, plus this one is a 2, plus 5, plus 2, plus 2, plus 3, plus 2, plus 3, plus 5, plus 29, plus 2, plus 2, plus 3, plus 3, plus 7, plus 41, plus 3, plus 2, plus 2, plus 3, plus 5, plus 2, plus 3, plus 191. And that gives us the number 326. So let's store that just down here. The next thing we're going to do, let me just remove all these. We're going to take another sum of the prime factors, but with a little difference. Instead of taking the sum of every prime factor, we're going to take the sum of every prime factor whose node second bit is a 1. So that's going to be this node here, this here, this, 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 this here, this here, this here, this here, and these two down here. Because there's a 1, there's a 1, these two are 1s, this is a 1, this is a 1, this is a 1, all of these are 1s, and this is a 1 right here. So we're going to take the sum of all these as well. 2 plus 2 plus 5, plus 2 plus 2 plus 3, plus 2 plus 3 plus 5, I think. 5, 2, 2. 2, 2, 5, 2, 2, 3, 2, 3, 5. 2, 7, 3, 2, 3, 3, 1, 9, 1. And that gives us a number 237. Let me just make sure I got that right. 2, 2, 5. Yep. 2, 2, 3. Yep. 2, 3, 5. Yep. 2, 7, 3. Yep. 2, 3, 3. Yep. 1, 9, 1. Yeah. All good. Okay. Now, what we need to do with these two numbers is we need to do a reductive modulo process on them. And we need to generate a string of numbers off of this. For now, for the most part now, we're done with the binary tree. We don't really need to do any work on it now. or any work involving it. So what we need to do is we take 326 minus 237 and record the result, 89. Then we take 237 minus 89. If the number that you've got, if your output is not smaller than the number, then you subtract 1 off the number that you're subtracting by and do the subtraction again. So we subtract 88 from this and we get 60. Then we do 89 minus 60 is 29. Then we do 60 minus 29 is 31. Subtract 28 is 3. And 29 minus 3 minus 2 minus 1 minus 0 minus negative 1. We're never going to reach 0. So what we're just going to do is put 0 on the end. Right, now what we need to do is we need to take our starting number up here and we need to convert it to another base, a base that is equal to however many of these numbers we generated from reductive modulo. In total we generated 7 numbers in reductive modulo, so we need to convert this to base 7. Base 10 to base 7. Plug that in and we get the number 3225. Now we need to split this number into pairs, and from here we need to make fractions where the smallest number goes first and the largest number goes second, using these numbers. These numbers here represent any number in sequence, where this one is a 0, this is 1, this is 2, this is 3, 4, 5, 6. So we need to take the second number, or well, the third number, over the fourth number. So 89 over 237. And then we need to take this number over here, 29 over 237. Where is it? Wait, no. No. Sorry, no. It's 60 over 89. Let me just make it easier. We assign these in order, minus 1, so we take number 3. Number 3 is 60, and we put it over 2. Number 2 is number 89. And then we take number 2, which is 89, and put it over 5, which is 3. Rearrange this so that the smallest number is on top. And now what we need to do is make a truth table with the number of bits equal to how many fractions we have. In this case we have 2 fractions, so we're making a 2-bit truth table. 0, 0, 0, 1, 1, 0, and 1, 1. And because there are 4 entries, what we're going to do is we're going to give each of these entries, we're going to assign the first 4 bits from here. We go back to this string here, and we're going to take the first number of bits from the remaining bits that we haven't used yet, so this lot here. We're going to take the first 4 out of this, put it down here, and we're going to assign each of these in order from top to bottom. 1, 0, 0, 0. What this means is which parts of the truth table are active or not. Any parts of the truth table that are active are going to be calculated for. The rest are not going to be used. So these 3 we can get rid of. Now we're left with just this. The truth table part, for each truth input that is received a true from this, which is only this one in our case, you will be taking the fractions and assigning them to each of their bits. If the input in this truth is a 1, then you just take the fraction as is. But if it is a 0, then you need to take the opposite of that fraction. So your fraction would be 89, or whatever your denominator is, minus your numerator, and that would make your new fraction. So these need to be flipped. 89 minus 60 is 29, so this fraction is 29 over 89. And 89 minus 3 is 86, so this fraction is 86 over 89. Then we need to take the product of these two fractions. So let's multiply these numerators together. Oh, wait, wrong place. 29 times 86 is 2494. And 89 squared is 7921. And you would do this for each true truth, and then when you have all of these big fractions, just take the sum of them. Now what we need to do is we need to flip this fraction. We need to take a 0 out of this. So we're going to put a 0 in our sequence, and we're going to flip this fraction on its head and take 7921 modulo 2494, which is 439. And we're also going to take 7921 divided by 2494, which is 3. 3 point this massive decimal. We're going to cut off all decimals, and we're going to take this 3 and throw it into our string. Now what we need to do is take 2494, our previous number, and we're going to divide it by the new number, 439. And that gives us 5. Let's throw that into the string. Take 2494 modulo 439, and that gives us 299, which we're going to use for the next fraction. 439 divided by 299 is 1. 439 modulo 299 is 140. Repeat the process. 299 divided by 140 is 2. 299 modulo 140 is 19. 140 divided by 19 is 7. 140 modulo 19 is 7. 19 divided by 7 is 2. 19 modulo 7 is 5. 7 divided by 5 is 1. And 7 modulo 5 is 2. 5 divided by 2 is 2. And 5 modulo 2 is 1. Then 2 divided by 1 is 2. And 2 modulo 1 is, well, 0. That's the end. Now we have this long sequence here. What do we do with this? What we need to do is convert each input to binary. So 0, 3 is 1, 1, 5 is 1, 0, 1, 1 is 1, 2 is 1, 0, 1. No, it isn't, it's 1, 0. 7 is 1, 1, 1. 2 is 1, 0, 1 is 1, 2 is 1, 0, and 2 is 1, 0. And this is what we're going to input into the module. For a 0, you input it into the left. For a 1, you input it into the right button. And for any spaces, you press middle. So this equates to left, middle, right, right, middle, right, left, right, middle, right, middle, right, left, middle, right, 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 middle, right, left, middle, right, middle, right, left, middle, right, left, middle, middle. At the end, you submit your sequence by pressing middle when you haven't pressed any other directions. So now we're going to submit this into the module. Left, middle, right. Right, middle, right. Left, right, middle. Right, middle, right. left, middle, right, 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 middle, right, left, middle, right, middle, right, left, middle, right, left, middle, middle.
This was exactly the way I'd like it.
And that is a solved modulo. Thank you for watching my Decay tutorial. I hope it has been informative. Ta-ra!